I speak in Korean, they translate as much as possible any issues, and it has the motion recognition and what is a panorama, and most of the, in terms of functionality, it's the same. And when I search the eBay, it's just a 50 bucks, and also the internal size is a 4 gigabyte, 3 gigabyte, and with the SD card is total 11 gigabyte. It's a little bit less than 16 gigabyte of the iPhone 6, but even design is almost similar as the iPhone 6, right? So I don't know why the kids are crazy about iPhone 6. Is it updated? It's updated. It's 8.02.
Yeah.
02. So it's a stable version where there's
How to use it.
So last class we have seen the classical, the critical, the synchronization problem. So we use the critical section to solve the problem of the synchronization. Then it's a simply when you enter the critical section, in other words, when you access the shared data with the other, when you have the other process, so you are going to lock, then use and release. That's the basic idea, no matter what method you are using. We have the software solution, and another one is the operating system solution, and third one is a hardware solution. Software solution, using the algorithm, we are going to, so there are three requirements of the synchronization problem solution. One is a mutual exclusion, which means only one process can access the shared data, and second is the progress. Progress means only the processes in the entry section will decide who will be the next one. And the last one is bounded waiting, so which means the eventually any process will enter the critical section. So based on such a requirement, we investigate the three categories of the solution. One is the software solution, so like such as a Peterson solution. Peterson solution is only for the two process cases, so which means it's not practically used in the real operating system, but it's a good solution for your understanding, so we can understand the critical solution problem, so such as by considering the three requirements of that. So then operating system provide the data structure. Okay, actually operating system itself also the software, but you do not use your own the program. Instead, it use the given the built-in the data structure. The last one is a hardware solution. Hardware means it's an instruction level. So instruction level, what's the instruction? Instruction is automatic, isolated operation, minimal the unit of the processing in the hardware. So using, but all of these are basically used based on the locking and release the lock, and there are algorithms to preserve the second and third the requirement. That is the progress and the bounded waiting. The last line, then using such a solution, we can solve the classical the synchronization problem, like we have seen the three of them, but we didn't take a look at details of the algorithm, but the philosopher problem and readers and writers problem and so on. Okay, then we eventually we can use a semaphore, especially the mutex lock. The mutex is the special case of the semaphore. It has the 0 and 1. The general data structure for the semaphore is it has a list of the integers, so you can access such a semaphore data structure using the wait and signal. Wait is the increase, and wait, yes, the locking, and the decrease, the minus, because you take the value, and the signal is the increase the value, which means the release the lock. So in case of the mutex, which means 0 or 1, so you need to, whenever you access the shared data, especially in the memory, so you need to get the wait first, wait, and then get the mutex lock, and you should release. Otherwise, it will be held by forever until you release it. But in your programming, system programming, now the application programming, you may not use a lot. Instead, in the system programming, you need to use both the wait and signal. However, if you use the signal first and wait, there's no problem in terms of using the semaphore. Semaphore is not only for the critical the section problem. Okay, it can be used for any other application or the system programming. So there's no problem in terms of syntax, but if you signal first then wait is the problem. Also, many of the system programming sometimes they forget to release the mutex lock, which means there's a wait to enter the critical section, then forget about the signal. So that caused a serious problem for the sharing data. So to address that problem, there is the researcher in the operating system. They try to detect or to solve such a problem of the mutex lock in the critical section problem. So monitor is one of them. Monitor is a high level. It's a data construct. Okay, so it's a software level. So which is not used a lot. Instead, compiler. Actually, compiler try to check whether they release the weight and signal correctly, appropriately. So we are not going to see the details of the monitor because you may not use such a monitor structure for critical section problem. It's usually managed by the compiler. Okay. We have a lot of things today. So you can go over the example of the such a synchronization for Solaris, Windows, and Linux system. Then the next topic is CPU scheduling. So we have learned about the long-term scheduling and short-term scheduling. During the chapter 3, the process management. What is the short-term scheduling? Short-term scheduling usually deal with very short period of the CPU time. For example, it's for the time sharing. On the other hand, the long-term scheduling is which job, which process will be selected. Okay, so CPU scheduling is example of such a short-term scheduling. So how we are going to share the CPU time. So that is a CPU scheduling. So as I mentioned many times, so since we have very limited computing resource, we need to consider some algorithm, okay, to maximize the utilization, to be fair with others. Also, we need to consider some priority and so on. The user service agreement. So in this chapter, we are going to talk about how to schedule such a limited CPU resource. So, idea is simple. Idea of the CPU scheduling is, so this such that, suppose that we have the CPU time. We have one CPU which has one core, which means that at certain time, only one thread of instruction can be processed. Okay, so CPU time. Then, if we just consider the utilization of the CPU, actually you don't have to worry about the CPU scheduling. You can assign one process and forever. Okay, that is 100% the CPU utilization. Right? Does it make sense? Yes. In terms of the CPU utilization, 100% is perfect. But you don't want such a thing. For example, think about the infinite loop. Okay? It will, from time to time, if your system is slow, your computer is slow, you may see that some of the process takes all the CPU job. Usually that is caused by the infinite loop or the synchronization problem. They keep waiting for the next turn up to enter the critical section. It's the same thing. So we are not going to consider such a thing. We try to share with others. How can we share with others? When we take a look at the program, what is a program? It's a sequence of instruction, right? So your high-level code, like the main and the integer I and the printf or whatever, this is converted into the series of instructions. It's a machine code, it's assembly code. Then when you take a look at this assembly code, you may realize sometimes you need CPU resource. What is a CPU? CPU is a computation, right? You read the data and store the data and subtract the increment or the register, something like that. So such a CPU bounded job, that's called the CPU burst. Okay? CPU bounded job. A lot of computation. Another type of the instruction is you want to read the data from hard disk drive. So for example, here the integer I is in the file. So you need to open the file and read the data. At that time, where is that the data I? This right? So CPU cannot read the data directly. Instead, you need to ask the disk controller, and this controller knows the address of the integer I, then access the data, then return to the CPU. How long it takes comparing to the CPU computation? It's very slow. Very, very slow. So during that time, it's called the I/O wait. You cannot do anything. Actually, without data, you cannot process the next instruction. So this is called I/O burst time. I/O wait time is called I/O burst time. So basically, your program series of instruction consists of two parts. One is the CPU burst time. Another one is I/O burst time. So during the such a I/O burst time, why don't we let the other process use the CPU time? So for example, this is for CPU burst time. So you allow this program process A use the CPU time. Then wait. So it's kind of idle of the CPU. During the time, request to the this controller read the data and get back. So at this time, why don't we call another process B? Then this process B also has CPU burst time, I/O burst time, CPU burst time, I/O burst time, and something like that. So this CPU burst time we assign to the CPU time. Okay? Then during that time, this process A will wait. So but it's not that simple when you have the 3 or 4 processes. Sometimes the CPU burst time is small and this one is longer. So by considering such a process status, the CPU scheduler will arrange which process will use the CPU time. That is a CPU scheduling algorithm, one of the most important algorithms used in the operating system. We will see what kind of such algorithm are proposed and used in the operating system. Basic idea is what? Always you like that algorithm. First in, first served. That's fair, right? So first in process means if the process is started earlier, then take the CPU resource. Then in case of such a condition, we will see when the CPU scheduler will select the next process, then the next earliest one will be selected, something like that. That's the first in, first serve. Usually first in, first serve, it looks like a simple, it doesn't look like the algorithm, but it's very simple and very well known and it works. So that is the basic algorithm we will see. By the way, such a CPU scheduling means arrange, okay, to maximize the computing resource. Is that the only scheduling algorithm? No, there are other scheduling algorithms like the disk scheduling algorithm or something other scheduling algorithm. But we can consider such a scheduling algorithm 2 categories. One is homogeneous. Homogeneous means it's the exactly same job it has. At that time, you cannot you don't have to schedule because they are all same. Okay? You don't have to worry about the scheduling algorithm. But the heterogeneous means so each process, each item, each object are different conditions. Also, we can consider such a scheduling algorithm two ways. One is you can actually increase the utilization. Okay. Another one is actually you cannot increase the utilization. There is a maximum. For example, this is the road. Okay. So this is a main road, main street, and it's a local road. And every day the postman deliver the whatever, then your package, and probably you realize if you stay at your home every day, almost the same time, the postman actually deliver the package, the same good, right? So probably the postman consider shortest, okay, shortest path or the fastest way, like this one or this one. So, but depending on the postman, sometimes it will take longer than the other, right? Sometimes some postmen like this. Okay? So depending on the algorithm, it can be shorter, it can be longer. So this is the postman style scheduling algorithm. What about the CPU scheduling? Even though you have the perfect one, can you increase the scheduling at the CPU time? No, you cannot actually increase the CPU time. CPU time is a fixed, it's a given CPU time. Then your algorithm is to maximize the utilization 100%. Okay? Even though you got the 100%, that doesn't mean that's perfect algorithm. You need to consider priority, you need to consider certain condition. However, anyway, this CPU scheduling algorithm cannot increase the CPU. However, this kind of postman delivery scheduling algorithm can be various depending on the algorithm. Okay, that's the difference. So in our CPU scheduling algorithm, not only just to maximize the utilization, we need to consider other factors, but in general, such as scheduling algorithm, any kind of scheduling algorithm are based on priority. So we will see why. So it's a different types of the priority. So which means depending on where you are going to focus on, the algorithms are various, but all of these algorithms are based on priority. For example, first in, first serve. What is the priority? Time to alive. Alive or time is priority, right? So, for example, shortest job first. What is the priority? Size of job. Okay. Shortest remainder job, we will see later. So, what is the shortest remaining job? So, the amount of the remaining job is the priority. So, any algorithm are actually is a priority based. Then you can easily understand. So this slide shows the idea of the scheduling. The job consists of the I/O bound job or CPU bound job. This means the x-axis increases the burst time duration. Okay, mostly I/O bound is a lot of time with a short period time. While on the other hand, the CPU bounded job takes a little bit longer, but it happens less than the I/O bounded job. So CPU scheduler is the short-term scheduler, as we have seen before. When this CPU scheduler will select the next process to get the CPU. The CPU computing power are the result. There are 4 cases. First one is switch from running wait state Second, running to ready, wait to ready, terminate. Can you remember the process, 5 process state? This one, new, ready, running, wait, terminate. Okay, so when you start the program and it's a new process state, when the process is ready to be executed, it will be in the ready queue. Okay, and also if this process is selected by the CPU scheduler, especially, that is called the dispatcher. Okay, dispatcher is a kind of function, part of the CPU scheduler. So dispatcher will select the one of the process to the running. So running state means right now I'm using the CPU resource. If the process is first case, running to wait. What's the example of the first case? Running to wait. In case input and output. In case you need to read the data from other device such as the disk controller, at that time you need to move the state to this one. So that is the first case. Second, switch from running to ready. When? Even though there is no I/O requirement, I/O operation, but after certain amount of CPU time, to share with other process for the CPU, then the process need to go back the ready state, ready queue. Okay, so that is the second case, switch from running to ready state, and switch from wait to ready. When? In case this controller interrupt, because this controller read the data, so we are ready. So this controller need to inform to the operating system how interrupt. Then at that time, this process will be ready to the CPU resource. That is the third one. Fourth, definitely if completed, is a terminate. So terminate means the CPU is ready to serve to other process. So in this case, you need to check. Okay. Also, sometimes you can run your CPU scheduler when there exists new process, new to ready. So whenever you have something in the change of the ready queue, you can call the CPU scheduler. And terminate, definitely, because it's empty in the CPU. At this time, the first and last one is called the non-preemptive case. Non-preemptive means, what does it mean, preemptive? Preemptive means is kind of resume of, which means backup. Okay? It can be done again the later. Non-preemptive means it should be completed, that's it, it's done. For example, the first case, terminate, is done. It will not be resumed. So it's a non-preemptive case. Running to wait. Wait means until this controller interrupt this one, it cannot be executed, right? So it's a non-preemptive, it's done. It's not mine. It's not the decision of the scheduler. Is done until the disk controller interrupt, then return the data, then it will be preemptive. So first case are non-preemptive case. Okay, it will not be resumable. Or the other 2 or 3, or in case the new process is coming into the ready queue, is a preemptive. At that time, you need to consider the access of the shared data and some other condition. So we need to implement actually dispatcher. Dispatcher is a part of the such as scheduling that select the next process. Actually, the overall CPU scheduling algorithm is mostly dispatcher algorithm. However, what the dispatcher is doing is it will select the next process. Okay, what happens when you select the next process? How can you manage such a ready queue or the database state? Do you need to copy all of this process? In other words, seek all the sequence of instruction to the memory, to the ready queue, something like that? You don't have to do this. What if you had to very huge build the process, like the Microsoft Word or the SQL Server? Whenever you have the context switch change, you need to copy all the instruction. You don't have to do that. Instead, you can manage PCB, process control block. Can you remember that? Process control block is a bit small data structure per process. It contains the important information about that process only. It doesn't keep all the instruction of that. Instead, it will keep the only the important kind of header information of that. So when dispatcher is doing the context switch means just the change the PCB, or whenever you move the state, PCB is moving. Actually, if there's a queue, this queue has a pointer of this PCB. You don't have to copy it. The only thing you need to manage is the address of that PCB. So, and also, it changes the switching user mode. So, can you remember that our operating system right nowadays has the two dual mode, user mode and kernel mode. Okay, so user mode requests a job, then the system code will be processed by the kernel mode because of the efficiency as well as the security issue. So that can be changed. However, because of such a context switch and the dispatcher has the little bit delay time. For example, so when you change the process, the dispatcher select the process B, okay? Then first is switching context switching, which means using the PCB information, you need to, this is the CPU, and all register information will be copied. And at first, the backup the PCB of A to this one, and keep all the record of the process A. Then the restore the register information about the process B from the PCB. Then should be ready. Then using the counter point the where is the next instruction. Then execute, resume the job. There might be little bit delay time. This time you cannot use the CPU time, which means it's not possible 100% utilization of CPU except infinite loop. Okay, infinite loop. There's no other process may get the chance to access the CPU resource. So this is called dispatcher latency. Okay, your goal is to minimize, but that's not the problem of the CPU scheduler. Yes, sometimes if you have a lot of change context switch in your algorithm, they may have some longer dispatcher latency, but sometimes you cannot handle it, even though you have the very nice algorithm. So in our study of the scheduling, we are not going to consider such a dispatcher latency. Okay? Instead, we are going to focus on only the algorithm. Then, how can we judge whether our scheduling algorithm good or bad? So one way is we already mentioned talk about the utilization. What is the utilization? How much the CPU resources are used. Like the 100% is the maximum and 0% is nothing. Throughput, what is the throughput? How many processes are processed? Okay? Per given time. Like the 1 minute or 1 second is usually used for batch job. Okay, and turnaround time is the total amount time from submitting a job and complete the job. Okay, it's a turnaround time. So then, if you have the multiple jobs, you can average them. So that is a turnaround time. What is a waiting time? When we have the CPU scheduler, process A cannot take all the CPU resource. Instead, this time and this time, this waiting time is called the total amount of the waiting time is waiting time. Then you can average by the number of processes. Okay, that is a waiting time. The next one is the response time. What is a response time? So probably you don't, whenever you call the cell phone service provider when you have the problem, at this time, when I activate my daughter's new phone, actually I mistake to put the SIM card number. Okay, one digit, only one digit. So that was the reason it's not activated. So I called the customer service center. Usually I should wait 5 to 6 minutes until the representative get the phone call. So usually such a customer call center, they try to judge their customer service level by waiting time. The waiting time does not count completion time. Just starting when I call to the customer center, so that is the starting time to when representative get my phone call. It's just the starting time. So waiting time is from submitting a job, then first response. Okay. So response time is very critical for such a service level. It doesn't matter how long it takes to complete the entire job. So think about your web. So whenever you visit the web page, like you have the eBay, Amazon, and the Google, they try to provide the first response as quick as possible. Even though, so that is the reason first show the text first, then image is the last one. Sometimes they are using the multi-thread to get the different types of different source of the data for one page, but they try to minimize such a response time. So there's a research that says that user will leave if response time is longer than 7 seconds, something like that. So that is a response time. So we can consider maximize the CPU utilization, yes. Maximize the throughput, number of processes, and a given time, and minimize the turnaround time for each process, minimize the waiting time, right? And minimize the response time to judge our process. The errors. What kind of errors we have? These are the incomplete list of them. So some of them are straightforward to understand. Okay? Very straightforward. For example, the first come first serve means the first alive process will be selected. When? The 4 cases that we discussed. When the process is moving from running to wait, running to ready, running to wait, and wait to running, and also terminated. Also, when there is a new process is coming. Okay? So at that time, we will consider arrival time. What about the second? Shortest job first. When dispatcher scheduling, select the process from the ready queue. Always, dispatcher will select the process from the ready queue, not the other queue. Okay? So we are considering ready queue. How? We select the process having shortest amount of job. Okay? How can we measure amount of job? CPU burst time. Okay? So CPU burst time. CPU burst time is such a amount of job. So then shortest job first means always shorter will take higher chance. What about I have very the long job that cannot be selected forever. So we are going to consider shortest remaining job. If this amount of job is already processed, we will take out that part. That's reasonable, right? Then still the longer job will have the less chance to get the CPU resource. The next one is priority scheduling. So we are going to assign the priority. This is the highest priority. No matter what size of job and how long it takes, it will be selected. This is a lower priority, then less chance to get the CPU resource. That is the priority. Yes?
Could you repeat it again? Priority schedule.
So if I'm going to explain again, I don't have to go over the rest of. This is just the introduction. So don't worry, we will cover details later. And round robin is a round robin. We are going to make a piece of the job, same amount of job for each process. Then take turn for per process. 1, 2, 3, 1, 2, 3, 1, 2, 3, something like that. That's round robin. Multi-level queue, because if we just consider one of the algorithm, it's not always. There's no general solution, perfect solution. We consider that in the ready queue, we consider multi-level queue. Then this is for first come first serve. This is for the round robin, something like that. Multi-level feedback queue is this one will be input of the next level. Okay, that's it. It's done. It's done. So then we will see the details of each algorithm. Actually, as you can see, all of these, the scheduling algorithms are based on priority. What is the priority of the first one? It's the arrival time. Second, the amount of job. And third, is the amount of remainder job. The first is a priority. Round robin is the order of the process. Okay? 1, 2, 3 is a round robin. And multi-level queue is a combination of the previous one. And feedback also. So in your first project, you need to implement this multi-level feedback queue. It's a programming assignment. Okay? So I'm going to explain a little bit more about such a multi-level queue. Before that, first come first serve. So the first top part is the process state. Each process has the first come first serve. We should know what? At least arrival time. Then next CPU burst time. Okay? So that is the reason process 1 arrival time 0. Then how many CPU burst time are needed? 24 units. I'm not sure that is a millisecond or second, just unit, think about. This is a unit, so 24 burst time. Then process 2 arrive, so this is using the timeline, so 5, 10, 15, 20, 25, something like that. And CPU 1 arrived here, process 1, okay? Process 1 is the only process in the ready queue. Then we take the CPU resource. Until when?
24.
You see? Until CPU, process 2 alive this time. However, which one is alive first? Still, process 1, because we only consider arrival time. So process 1 will take all the CPU resource until completed. Okay? So which means it's a 24. 24 here. Then in the ready queue, how many processes are there?
2.
So this is process 2 alive, the time 1, and process 3 and alive time 2. Which one is the next? Process 2, because it's alive earlier. Then process 3. Then we'll take the CPU resource like this. Then the next is process 3. This is called Gantt chart to visualize the CPU scheduling algorithm. This is a CPU time. CPU time, and this the width, there's no meaning of the width. Just the process 1 take the disk, process 2, process 3. Can you see the dispatcher latency? Which means any idle time in between. No, we are not going to consider dispatcher latency in our algorithm. Just small amount of time. So to focus on the algorithm, we ignore. So this is the first come first serve, straightforward. It's very too easy to understand. Yes.
How about the priority? When we are processing the P1 and P2 and P3 are waiting in the ready queue.
Yes.
But what if P3 have the priority?
That's a good question. So that is the reason we have the priority-based scheduling algorithm. Next. Yes, here we will talk about. So you already know what is the next one. Okay, good question. Because first come first serve is very simple, but such a problem. So for example, the process 2 is should work. For example, think about scheduler itself is actually the process, right? So it should get the higher priority. Otherwise, it cannot arrange the CPU. So this scheduler should get higher priority. Something like that. Anyway, we will see details of it. So after we make such a Gantt chart, we need to evaluate whether this one is good scheduling algorithm. How can we evaluate? We can use 5 the evaluation criteria. Among them, most frequently used one is waiting time. Okay, what is the average waiting time using such a first come first serve? What is the waiting time of P1? 0. What about the P2? It's arrived 1 and started 24. 24 minus 1 is a 23. Then what about the P3? It's arrived 2, but it's executed 27 is a 25. Total how many? 48 divided by number of process. In using this algorithm, what is the average waiting time? 16. Okay, so it has the 16 waiting time.
So why the process is 3 with the time 25?
Excuse me, I cannot hear you.
Oh, the process 3.
Process
with
3.
time is 25.
25.
How we can get this number?
How can we get
25.
25?
Why it's 25?
Its arrival is at 2.
Arrival plus?
It's arrival time 2. Okay? So arrival means it's to enter the waiting queue time to this time. Then executed 27. What is the waiting time?
Okay, thank you.
So it's a 27 minus
2.
2. So 25 time unit. Then we can average by the number of process. This is another example. It's the same CPU burst time as the first example, but different order. So we are going to process P21, P2, arrive the P2 first, time 0. P3 arrive the time 1 with the P3 CPU burst time, and P1 arrive the time 2. Okay? Then this is a Gantt chart. It's straightforward because it's the non-preemptive, which means once the process started, should be completed. Okay. What is the waiting time of P2? 0. What is the waiting time of the P3?
2.
It's a 3 minus 1, 2. And what is the waiting time of P1? 6 minus 2. It's a 4. So 4, 0, 2, total 6 divided by 3. What is the waiting time?
2.
Average waiting time is 2. For the same amount of CPU burst time, this one has the 16, this one has the 2. Why? Waiting times are so different.
Schedule
scheduling algorithm is the same. Order is different. Order is different, which means this one long process started first. This one short amount of time, short process started earlier. So usually first come first serve is simple to implement. However, in case the long process started earlier, then the other process should wait longer. It's called the convoy effect. So short process actually hide behind the longer process. Okay, how can we address such a problem? We select short process first. That is the reason the next one is shortest job first. Okay, so it's a simple, very fast, because you just consider arrival time. Also, it doesn't have to be a lot of context switch. Once it's started, will be completed. Okay, the problem, it has a longer waiting time in case long process is running. So we need to address that problem using the next algorithm. It's a shortest job first, SJR, scheduling algorithm. So in case dispatcher or scheduling is activated when 1, 2, 3, 4, and 5, the new process is coming. At that time, you can just consider current status of the process. Current status, what do you consider? Amount of job, CPU burst time. Okay. By the way, we can consider any CPU scheduling algorithm by two. One is non-preemptive, another one is a preemptive. As I said, preemptive algorithm means it can be restarted, resumable. And non-preemptive means once started, should be completed. So, for example, first come, first serve. FCFS algorithm is a non-preemptive or preemptive? The previous one. This. It's the non-preemptive one. Once started, it can be completed. Why? Because it considers only arrival time. On the other hand, if you want to stop in the middle, then start again later, is the preemptive algorithm. Usually, the preemptive algorithm require more context switch. Okay, it has longer latency. However, in our algorithm, we do not consider such a latency. So we will see the non-preemptive shortest job first. In shortest job first, there are two types. One is the non-preemptive. What does that mean? Non-preemptive shortest job first. Once it is selected by the scheduler, it will be completed. So first we have 4 process status. Process 1, arrival time is 0, CPU burst time. Process 2, arrive 2 with the 4. 3, 4, arrive time 4 and with the CPU burst time 1, and so on. We have 4 processes in the system. So shortest job first. So this is the CPU time. We are going to manage the ready queue. This is the ready queue. So in time, current time, this is a current time. It's a 0 and current time, each process is in the ready queue.
P1.
It's a P1 with arrival time 0 and CPU burst time 7. So this will be selected. How can we select? Shortest job. 7 is the shortest job because there is only one process. So process 1 will take the CPU resource. Okay, Up to where? When?
7.
It's a 7. Why? Because it's a non-preemptive. Even though there is the event, we talk about the 4 plus 1 event. One is from running to ready, running to wait to ready, and the terminate, and the new to ready. Even though there is an event, we do not stop the current process. So it will take the 5 CPU resource up to 7. Meanwhile, process 2 is alive with when 2 CPU burst time 4. So let me do nicely. Right now we do not have P1, so P2. And arrival time is 2, CPU burst time is 4. The next one is P3, arrival time is